Okay, welcome back everyone. In this video we're going to be looking at a two-dimensional example of using Newton's law of gravity. And so this is number 44 from chapter 13. And so we've got two masses, M1, which is 60 kilograms, and M2, which is 80 kilograms, which are separated by 3 meters on the y-axis. Then we have a third mass of 5 kilograms, which is 4 meters away from mass 1 on the x-axis. So that gives us a hypotenuse of 5 meters, and similar to other problems that we've seen, this gives us a nice value for the sine of our angle, 3/5, and the cosine of our angle will be 4/5. Okay, so the first thing that we're trying to find is the net force acting on object 3, on mass 3. And so if we think about this, we are going to have two separate gravitational forces. We're going to have the force of 1 on 3, which is directed away from 3 towards 1, and then we're also going to have the force of 2 on 3. And so the strategy here is I'm basically going to calculate each of these forces separately and then stick their components into a table in order to find the total x and y components of the net force. Then I'll recombine those into a triangle to find the net force. So we're going to use Newton's law of universal gravitation, and that means that the force between 1 and 3, or rather of 1 on 3, is equal to g m1 m3 over r13 squared. And you can plug in all the numbers for this, but we're going to get 1.25 times 10 to the negative 10th newtons, and that's going to be in the negative I hat direction. And that matches with our diagram. So I'll do this table a little bit bigger. Basically what that gives us is F13 with negative 1.25 times 10 to the negative 10th newtons for the x component, and then the y component will be 0. So now we do something similar for the force of 2 acting on 3, and that's g m3, m2 times m, which is really m3, over r23 squared, and that's going to actually get us about 1.07 times 10 to the negative 10th newtons. And you might notice that that's less than what we found for F13. And the reason for that is that even though we've got more mass, about a third more, we've got more distance. We've got a quarter more. And distance has a much greater effect because of our 1 over r squared. Okay, so now we need to take this and split it up into components. And so we have F23 in the x direction is going to be F23 cosine theta, but we said previously that cosine theta would be times 4/5. Okay, so if I put F23 in my table here, I'm going to get negative 0.85 times 10 to the negative 10th newtons. And then if I do something similar for F23 in the y direction, I'll get F23 times the sine, which is 3/5, and that's going to be positive 0.64 times 10 to the negative 10th newtons. Okay, so then what we do is we add up our totals, and we get negative 2.10 times 10 to the negative 10th newtons and 0.64 times 10 to the negative 10th newtons. And so what you might see is that we have basically a triangle that looks like this. And I'm dropping the times 10 to the 10th. Okay? And so our net force is the hypotenuse here, which is about 2.20 times 10 to the negative 10th newtons, and it turns out that this angle is about 17 degrees above the negative x-axis. Or if you like, you could write it as at 163 degrees. Okay, now you could also do this with law of cosines, but that might be a little bit messier with the algebra, but you're free to solve this whichever way makes sense for you. And so now in part B, what we're going to do is we're going to try to figure out a point on the y-axis where the net force is 0. So in other words, is there a place where we could put a test mass, a mass little m, is there a place where we could put it so that the net force would be 0? And so again, what we would have is the force of 1 on 3 and the force of 2 on 3, and we would want those to be equal and opposite. And what we could do is label the distance vertically on the axis to the mass as y, and so that means that the remaining distance would be 3 minus y. Okay, so that allows us to set up our equation that F13 must be equal to F23, and so we have g m1 times m over y squared equals g m3 times m over the quantity 3 minus y squared. So we get some nice cancellation, and this turns into 60 over y squared equals 80 over 3 minus y quantity squared. And we're just going to take the square roots. So this means that y times the root of 80 is 3 minus y times the root of 60. And if we solve this for y, we get approximately 1.39 meters. And if we think about this, this makes sense because we have the 80 kilogram at 3 meters and we have the 60 kilogram at 0. And so we want to be closer to the 60 because its mass will have less of an effect, so we need the distance to have more of an effect. So it won't quite be right in the middle. It'll be a little bit closer to the smaller mass. Okay, so hopefully this helps when setting up gravitational force problems.